All right, let's go ahead. So let's discuss this one. So what did you guys come up with so far? You guys can stand up and make them feel better if you want. They don't have to stand alone.
Well, this bar is on two sliding collars on basically a shelf that is fixed.
Okay.
So we knew that each sliding collar is going to have a translational instant center and a rotational part because this bar is rotating and sliding at the same time.
Okay.
So the rotational is at the connection point where the collar hits the solid part for A and B.
Come on, guys. Can't see from back there.
And the translational part is going to occur at some line perpendicular to it at infinity.
Okay.
And since this happens for both of them, we concluded that the instant center of A and B is where these two intersect, right up there.
Okay, I think you got some things that are true and some things that are false. What do you guys think? Anybody else? What do you like or not like about this?
Oh, this is 34, by the way.
I like the 1B, that translation that goes up.
Yeah, I don't like the 1B.
Why is that?
I'm just trying to be antagonistic.
Okay.
Thanks.
I'm trying to get someone to argue or say, hey, why is it this way or why not? I'm trying to get you to think. Do you think 1B is in the right place? What is 1B? What does that instant center indicate?
Well, it should go down,
It should
right?
be, it goes along the line.
Goes along the line. Should be what?
It shouldn't be, it's not a pin connection, so I don't think it should be right where the two meet.
Okay. Okay, we're on the right track. If I label an instant center 1B, what am I saying about that point?
That point 1 and point B are on that line.
No, their velocities are the same.
The velocities are the same, right? That's what you're
One's not
saying.
moving, but
What
these-
velocities are the same? Velocity of body 1 and body B at that point. That's what you're saying, right? Is the velocity of body B and 1, what is 1? 1 is ground. Is the velocity of body B and ground the same at that point?
No.
No, right? It can't be. Does that make sense? I don't feel bad about it. It's no big deal. The time to feel bad is if you mess it up on the exam. Okay, so don't do that.
So why would they not be the same?
Because B's
Because
sliding
one-
and the ground's not.
So then 1A doesn't,
So neither 1A or 1B are in the right place. Let's erase 1A and 1B. Now you guys have a good thing there, actually. You've located some pivot points, and those pivot points are actually really good. So don't erase the pivot point. Let's put that back up there. In fact, where's our green pen? Can you hand us the green pen? Thank you. So that pivot point is important. What is that pivot point? Well, not all the bodies are named, right? We've got a body A, a body B, a ground body, but there's one more body up there.
The link itself.
The link itself, right? So let's label that other link C. So the first step in figuring out where instant centers are located is to name your bodies, right? You got to name all of them. How many bodies do we have here? Four, right? This is a 4-bar mechanism. 4-bar mechanisms are exceedingly common. This is another one. Now we've got an ABC. Now what do we call these points?
AC, C.
Yeah, AC and BC. Okay. Now let's make them IVC and IAC, because those are instant centers. Okay? Good. Thank you guys for being patient with us. Okay? I agree with that. Now let's go back to I1B. There must be some point where ground and body B have the exact same velocity. Where would that point be?
it'd be infinity.
At infinity on a line perpendicular to the ground through that point. That's exactly where it's at. Oh, good, thank you. Now, yeah, I agree with you so far. That's good. So what we really need to do is add a vertical line. You've already got one there, that green one. What note do we need to put on that line?
I1B at infinity.
You got it. That's it exactly. And I like to put a double arrow on it, or just beside it or something, so that I remember that it's at infinity on that line in either direction. It doesn't matter which direction. Okay? Now for a little bit more difficult one. What about 1A? Where's that at?
Same line.
Same line?
No, perpendicular.
Perpendicular to what? To the ground. Where?
Point A.
At 1A. That's right.
Someone else wanna go now?
Go ahead. Somebody else be confident and be on video for us. Have the whole team do this. Is it up and down?
No, it's perpendicular.
Perpendicular to the ground where A is sliding.
Just extend your.
So it's like a normal force.
Would be the
Your
dotted line
ground
we already
is
have?
this
Yeah.
way.
The ground's
That's
that
what
way.
I'm saying.
So we want a line perpendicular to the ground. Right?
So just
You're right.
extend parts, right?
Yeah.
Put it on the bottom side. There you go. Good. That's right. Good job. So where is I-1A then?
At one.
At infinity on that line, right? So how do we add a note to that? What do you think? Good. And where's the double-headed arrow? Good. Perfect. See? So it's easy. Good job. So what all have we found so far? 1B, 1A. Good. What other instant centers would there be?
1C.
1C and B.
1C and AB. Okay. Now we've got AB listed up there. Is it correct?
Yeah.
Prove to me that it's correct.
Yeah.
I
Draw a
agree that
line
it's correct.
perpendicular to the points and then extend them out.
Okay.
So, AB would be a function of A1B,
It's the,
ACB.
I'm waiting for you guys to see it.
it's the intersection.
It is the intersection, that's right, but what instant center is it? Is it AB? That is an instant center, but is it instant center AB? What do? We use the Kennedy-Arnold theorem, right? I keep talking about canceling the common. It's 1C, isn't it? Is it? Show me why that is instant center 1C. Anybody that sees it.
AB cancel out because they're both part of it.
Well, come up and point to it.
You have,
The price is right, come on down. Anything incorporated in
this
this.
one would be point here and these cancel out, so you're
Okay, well,
just,
what cancels? Go a little
that
slower.
point A and the point B's here.
Well, it's not point A and point B that we're connecting, right? It's the instant
Yeah.
centers we're connecting.
The instant center on the lines, the A's and the B's cancel out, and you're left with C.
Okay, let me go a little bit
So it's
slower.
A, B, C, and then you have
What you're saying is
AC.
1A is on this line,
Yeah.
AC is right here. If I connect AC to 1A,
Yeah.
there's the line that connects the two. The common between the two is A.
Yeah.
Cancel that C. That's what you're saying, right?
Yeah.
Okay, good. And we can do the same thing for the other line, okay? Mr. Long, you've been very quiet. Can I get you to show us that for the other one?
Show what?
Show us how that this line is a line for 1C. How do you know that?
I don't know.
You don't know? Okay, all right, well, let me help you just a little bit. We know that's wrong, all right?
Okay, that's fine.
No, I'm not trying to embarrass you.
Yeah, that's fine.
We all get
I'm
embarrassed.
always embarrassed. My secret.
I am too. Sometimes I can't think right. And I don't know the answer to my own questions sometimes, and I kind of wait for a little while and see what people will say. And then it comes to me. So I feel a little embarrassed too sometimes. So you're right, that's 1C. How do we figured it out that 1C is on this line because we're connecting 1A that's out at infinity, which is kind of hard to think about, right? We're connecting it to AC, and that's this line, and then canceling the common is canceling A. So 1C is on this line. Can you show me two other instant centers we've connected together that indicates 1C is on this line?
I1B.
Good. Connected to?
What?
Connected to what other instant center?
Oh, IBC.
Good, right. Because you cancel the B, and look, we've got 1C again, right? So 1C is on this one, and where those two intersect, that's the instant center, okay? We've got one more instant center. Why don't you mark that also? We've got, thank you. We've got AB to find. How are we going to find AB?
Couldn't you just use C?
What's that?
Couldn't you just use C?
If we just use C, I want you guys to get away from thinking about the links themselves. You gotta start thinking about the instant centers, okay? In fact, you know, I just realized a good way to teach this. What I should do is draw the mechanism in SolidWorks, locate the primary instance centers, okay, because that's based on the mechanism, right, where there's joins and pairs and things, and then make the mechanism completely disappear, and all you see are instance centers, right? Because if all you saw were the instance centers, you would begin to think, well, okay, which ones of these do I connect together to indicate the Kennedy-Arnhold theorem? Does that make sense? So let's forget them. In fact, you know what? Let's do it. We're going to be radical here. We are going to completely eliminate the mechanism. And see if that helps our thought process. Okay? I'm going to make it even more effective. Can I borrow that green pen? So this was IAC, right?
Yep.
And this one was IBC. All right. Now forget the mechanism. Now what instance centers do we connect together to find AC? I'm sorry, AB, excuse me.
One AC and one BC.
Okay. AC, BC, and 1B, 1A. Good. Okay. So, who wants to volunteer? Any of you guys can join us on this. This is just practice for the whole class. Anybody have an inspiration here?
Draw a little line, A, C, B, C.
Mr. Clark, come on down. The price is right.
So, to connect these two,
Okay, AC and BC.
these two, which would
Okay.
be that instance center and that instance center.
So we just need a line through them. Good, and label that line and let us know what you're looking for.
Okay, so this is, somewhere on this line is the, is IAB,
I agree.
so, somewhere,
Somewhere,
yeah,
right.
this way or that way.
Well, I don't know if I like that because that kind of suggests that infinity. How about if you just put a curved arrow up to the line from the instance?
Okay,
Yeah, so somewhere there. We don't know where.
okay.
Good.
And then we need to find 1A and then the line between 1A and 1B, which is, so this is 1A,
One
is
is
at
at
infinity,
right?
and 1B is at infinity. So where they connect, or would be that, actually, I'm not entirely sure.
Okay. I'm not entirely sure either. Remember those moments I told you about where I'm not sure what the answer to my own question is? Now is one of them. Okay? We have kind of a problem here, right? Because we're trying to connect two instance centers that lie at infinity. How do we connect them?
Wouldn't they just be parallel lines?
I think it would just be parallel lines. I think what'll end up happening is if we try to connect 1A and 1B, I think we're gonna end up with a line that's parallel with this one. That's what I think is gonna happen.
Yeah.
And if that's the case, what does that say? I mean, what instance center are we looking for? We're looking for AB, right?
Yeah.
So we're looking for a point where both link A and link B have the same speed. And those links were the two sliding blocks, right? So
Does
maybe
not
I'm wrong.
exist.
But yeah, I think what it says is that, yeah, I don't think, because if we have a line parallel to this, it never intersects, right? So
Yeah.
basically, they're not moving the same speed. There's
It would
basically
be
no
possible
point.
because B's on a flat surface.
Right,
And so
and they're both
they
just
only have Y,
translated.
yeah, it's just
Right.
translated.
So there's no point where those two are going the same speed. Okay? That's perfect. Sometimes that happens. Sometimes because of either redundancy or because of trying to connect two instance centers that are both at infinity, you can't find an instance center. Now, if I thought about it a little longer, I might be able to come up with a better answer than that.
Wouldn't it just be C at the bottom though, when, like at the point at 180, where it's at the bottom, there would be no, it'd just be in the horizontal. So
Right, but-
when B gets all the way to the bottom of its
Yeah,
slant
but
or
wait, be
wedge.
careful with that. You said when B gets all the way to the bottom. We're not interested in that. We're only interested in this particular position.
Okay.
Okay? That's something really important to grasp here, is that we're only talking about instance centers at this one particular position, okay? Because as soon as the mechanism moves, all the instant centers move, and all those ratios change, and so the velocities change, okay? So that's really important. Thank you for
So,
bringing
but at
up.
that point, if you're able to relate AB, would 1C cease to exist?
At this point right here,
No, at the point where B is at the
well,
bottom.
that's a different position. We
Yeah.
can consider, if it's at the bottom, they're both, everything's just translating.
Yeah.
Right? So that's kind of a trivial thing to figure out, right? Could we still relate A to B? Like, let's say that we knew the speed of the link that was at the bottom, right? The link that was at the bottom was B, and so it was moving, let's say it's just moving off to the right, okay, with some velocity. Could we figure out the velocity of C? Is that doable? You need to write down a couple more equations. Thank you, guys, I appreciate it. I'm gonna make you stand in front of the class for the rest of this. And you guys are getting ready to sit down, that's fine. I guess I kind of feel like when you sit down, you disengage, you just kind of sit there and watch. And that's okay, but I want you to keep thinking with me. Because you need to add another equation to your sheet, okay? Remember the velocity equation I gave you back there on the previous problem? Okay. Well, that velocity equation is something you need to add to your sheet. So if you're interested in the velocity of a generic body, J, how do you calculate the velocity of that body? Well, it's just omega r, isn't it? Right? It's just a tangential velocity. So what omega? Well, let's talk about the angular velocity of body K, and then what instant centers do we need? Well, I'll go by analogy from the equation I've got on the back. We need the instant center from 1 to the rotating body K, and we need the instant center between the two bodies, where the two have the same speed, which is JK. Okay? So add this equation to your sheet, please, along with the angular velocity equation we last time. Okay. So if I want the linear velocity of a body, or the angular, like for example, let's say that we're given that the velocity of v is 10, what are we in on this, feet per second, or what was the problem? Problem was 34. Is it English or
Meters
metric?
per second.
Metric, okay, so meters per second. Did they give us a speed? I'll try to match it if they did.
2.4 meters to the second to the right for color B.
For B, so 2.4?
Yeah.
Okay. All right, fine. So 2.4 meters per second. Could we figure out the angular velocity of the link?
Yeah.
What did they call the link? BC? Or something?
AB.
AB is what they called it? Okay. So we'll switch. Instead of calling it link C, we'll just call it AB. Okay, so we're consistent with the problem. Well, look, now the only unknown is the angular speed of AB, isn't it?
And the angle they give you is 20 degrees.
Okay. So we need the distance from, let's see, I tell you what, let me back up. I hate calling bodies AB. Can I call that C again? Mm-hmm. Okay, and then plug in everything here. So K becomes C. Okay, and J is B. So I need the distance from 1C to BC. Well, that's easy. That's just this distance. Okay. That's the distance I need, and I could calculate, since I know that speed, I could calculate omega C. Okay. So to get that distance, is it easy geometrically? What kind of geometry do they have there for us? Tell you what, I'll draw it in SolidWorks. For Mr. Hubbard's sake, I'll move the video camera over. We'll just make a real quick new file. What is this, 34? Yes.
Can't you just take this, like the sine of the angle or cosine of the angle times the hypotenuse to get the length of the side?
Why don't you try that, and I will try this, and we'll see who gets there first.
Okay. 450 times the cosine.
And let's see. Has to be some other geometry here. Oh, there it is. There's the angle I'm looking for. We'll pull that down to here. Converge the two. Put our 60-degree angle here and 20-degree angle there, which is given in the problem statement. Connect these two. And the question we had was, what's the, hang on just a second. Can't talk and draw at the same time. There we go, that's it. So the distance is the distance from here to here. That's what we care about. And let me change our units. 398.05 millimeters. Is that what you, whoever was saying, I don't know who was talking to me. Is that what you got or not? Okay.
It wouldn't have helped.
Wouldn't have helped, okay. That's why I like using SolidWorks as a calculator. Even something that's fairly simple in geometry like this is a little bit complicated.
Because those are different angles than the angles underneath of it, so.
Yeah. So 398.05 millimeters is the distance from, now for Mr. Hubbard's sake, we've got to go back. My battery's low, hopefully I don't lose him. That's the distance here, and now we can figure out the angular speed of c. Once we get the angular speed of c, we'll be able to use that to calculate the linear velocity of I think actually that's not VC, is it? Isn't that VA? I messed up there, right? VA then would simply be equal to omega c multiplied by I1, I1c to, it won't be BC, it'll be AC this time. Okay, so hopefully that'll be enough for Mr. Hubbard to continue to figure this out. So all we need is the distance from 1C to AC. 1C we know is here, AC is here, so we just need that distance now, right? So let me put that on there. Hopefully I'll get it before the video camera runs out of battery. So from here, here is the other length we need, is 488.28. Okay. All right, so let's go ahead and calculate. Omega C equals velocity of B divided by I1C IBC. Okay, we know velocity of B is 2.4 meters per second. We know that I1C IBC is this distance, which is 398. What if we do it this way? 0.39805 if you want it, meters. Okay, so that will give us radians per second for the angular speed of C. Is C rotating clockwise or counterclockwise? Pretty easy to figure out from intuition. Isn't C moving like this, right? So isn't that a counterclockwise rotation? Okay. All right, anyone have a number for me?
6.03.
6.03. Radians per second. Good. That seems reasonable. Now how about the linear speed of A? Well, now that we've got the angular speed of C, 6.03 meters per second, all we have to do then is, let's see, there's a link C, it's not over. All we need is the distance 1C to AC, but that's